is Luis Cunha. I'm a PhD student at the University of Minho, and today I'm going to present the work we've been doing the last few months, which is an open source RISC-V input-output physical memory protection IP. So I'm going to start with a bit of an introduction over why the IOPMP specification is needed and an overview of the actual specification. Next, I'm going over some of the implementation aspects we have, and finally, the evaluation we performed on the developed IP. So, the introduction. Memory protection is a recognized security capability in the RISC-V community, and its main purpose is to prevent a process from accessing memory that has not been allocated to it. There are currently multiple ways to enforce this, but the main one, as part of the privilege specification, is the physical memory protection, or PMP, which enforces this memory protection at the hard level. So, for example, when you have a malware running in a rich execution environment, it tries to access, for example, another application that is running, and the PMP blocks these unregulated transactions. However, the PMP only enforces this memory protection at the hard level, meaning the other devices connected to the bus are completely unsupervised. So in the same example, the malware still running in the rich execution environment can now configure a DMA maliciously and have the DMA perform the unregulated transactions for it. This, of course, compromises the entire system, and, for example, even a trusted execution environment that may be running completely isolated can be targeted. So, to solve this, the RISC-V community has been working towards the specification of the input-output physical memory protection, or IOPMP, which basically mediates and manages device access to memory by performing permission checks, like the PMP does at the hard level. The same example, the malware can still configure the DMA maliciously, but now the unregulated transactions are completely blocked depending on the configuration of the IOPMP. Of course, as the name suggests, the IOPMP enforces this at the physical address space, right? However, as predicted in a platform security model, it can be used all the way from MCU-like devices to APU-like devices, as sort of this example. So, the IOPMP specification, I won't go over, just gloss over it. Basically, it mediates bus access from devices. As I mentioned, it has multiple device support, meaning a single block can control multiple devices. It features 5 operation models to cater to different system requirements, and features a different priority scheme than the PMP. So, it defines 3 main structures, and this is the part that interests. So, it defines an entry, which defines a physical address range and a set of rules, like the PMP does. It defines a memory domains, which allow us to partition the entry array, which stores the entries, into different regions, and the source identifiers, which actually identify the device that is making the transaction request. So, you receive a transaction, you extract the SID, use it to access the source to MD tables, you extract the memory domains that belong to this source. Next, with those indexes, you access the MD config table, and finally, you have the entries to assess your transaction. So, a little overview of our implementation. You can find on the figure a little block diagram, an overview of the microarchitecture, and on the table, you can see the features we currently support. So, we support the full model, which uses the previously mentioned tables to their fullest, and we have all of the mandatory behavior currently implemented. Additionally, we support top-of-the-range entries, programmable priority entries, and the source enforcement mode. So basically, the microarchitecture, the communication handlers, extract these transactions information that we receive from the bus, the SID, base address, all that you need to validate the transaction, and we pass this information on to the matching logic, which actually calculates the valid entry indexes and validates the transaction. Here we had 2 approaches. Basically, more parallel approach, like normal PMP implementations do. But of course, this entails a lot of performance because we do all of the checks combinationally. The overhead is very small, but in terms of scalability, it starts to increase non-linearly, right? So we had another approach, which was a more sequential approach, and it was the one we decided on, as one of the main goals we had was the scalability and modularity, because when you start to add hundreds of entries, maybe support dozens of sources simultaneously, this starts to become a problem, adding more and more, not having scalability starts to become a problem. So basically, what we do is we have entry navigation. Basically, the control logic gets the first index, valid index, in this case is the entry 0, and we go from there, entry 0, entry 1, all the way from the entries that are currently valid. For example, in this case, the next valid entries are entry 5, so we would go from entry 1 to entry 5. And of course, this entails some performance penalties that I'll talk about later, but this is the main gist of how the IOPMP we implemented works. So, how do we validate a transaction? Basically, we go over the entry array, we get, for example, entry n, and we match the base address. When we match the base address, we get the final address of the transaction. We check if this same entry still can be used to validate this transaction. And if yes, we check the permissions. If, for example, it's a write and the permissions allow a write, we allow the transaction. And the entire transaction can be validated within the clock cycle after, of course, finding the corresponding entry with what I mentioned earlier. So we performed some evaluation on the IP. Basically, we started by a functional evaluation. We had to validate that the IP worked as we intended. So we started with a variated model and then got into a model in a Genesis to FPGA. And basically, we tested two configurations for this, of a single CVA6-based SoC, one with an IOPMP in source enforcement mode. Basically, it ignores the source checking, managing a single IDMA device, and an IOPMP managing multiple pulp IDMA devices, as the figure suggests. We currently have multiple validated software stacks. We validated in a custom bare metal framework. We developed in-house OpenSPI plus bare metal and OpenSPI plus Linux, where OpenSPI performs the configuration of the IOPMP at boot time. So we made some resource evaluation on the actual hardware resources we use. And as we had hundreds of configurations to test, we settled on some ground rules, so the same number of MDs as supported sources, and for each source, we have 8 entries. So as we can see in the baseline, we have 1 source, 1 MD, and 8 entries. And the main point we want to take from this is that as we increase the number of sources, of course, the number of resources in our implementation also increases. But for example, from the baseline into the X32, so we have 32 sources, the number of resources didn't scale linearly. We don't have times 32 the amount of resources we had previously. And to put another takeaway, to put this into perspective, is that, for example, when we use this implementation of the IOPMP in a CVA6-based SoC, is only represented a fraction of the overall SoC, and with our most resource-intensive configuration. So our implementation introduces latency into the system. So to assess this, we had a custom DMA device performing independent store and load operations of a word, a double word, and a quad word into the system. Basically, to assess the clock cycles we have here, we have a bare metal application running alongside it, which basically starts indicates the custom DMA to start the transaction and wait for it to end. And actually, the time that it takes, we count the clock cycles using the clock cycle in the CPU. And as we can see here on the chart, it basically illustrates what I mentioned in the implementation and what we were expecting. As the amount of entries increases, the actual entry that validates the transaction, as we know, for example, as I mentioned in the implementation, we have several entries. If we are on entry 2, have a validation, we don't need to go to entry 3, 4, and 5, so the performance penalty is much lower. But as we can see here, as we increase the amount of entries and the entry that actually validates the system, the amount of clock cycle penalty increases accordingly, as we were expecting. However, when we put this into perspective, into an actual more macro view of the system, and to test this, we implemented almost the same configuration with a bare metal and a DMA, and the same configuration with a DMA, but now an application running in Linux, which actually is controlling this DMA. And what we discovered, as well we say, with more complex software stacks and more complex workloads, not the words, double words, small transactions, the performance penalty is much less noticeable. And for example, we only, with the Linux plus DMA, we only expected and got performance penalties only up to 3%, even with 64 entries, which is quite a lot of entries for a single source. So the main takeaway that we want to take from this presentation is that we designed and implemented the first open source IOPMP IP, which is compliant with the version 1.00 draft 5 of the specification. Currently, the specification is not ratified, but the main concept and the main works, or how the IOPMP works, is pretty stable, I would say. So I want to finish with a call to action. We actually have the IP in the repository, so please go there. These are the links. If you want to, I'll just let you take a picture. But we have a basic IP of the actual implementation, and we have a CVA6-based SoC with the actual IOPMP and the DMA. Thank you very much. That was it.
So we've got time for a question. Yeah. For several questions.
What's your next step?
Currently, we are a little stopped, right? The specification doesn't change very much, and the IP is quite stable as it is. So we don't predict, for now at least, any more changes. But as the specification actually starts to reach a more mature state, right, we plan to keep on implementing. And as the call to action is actually for people to use the IP and to extend it, that is the main point. I don't know if...
Thanks. Oh, there.
Hi. Thanks. In the verification that you perform, what measure of completeness for the verification process do you use?
Sorry, I didn't understand.
In the verification process, how do you measure how complete the verification is?
So we only perform the functional validation of the system, but I can go a bit back if it will take a little time. So, but the software stacks the validated software stacks that we have here, the custom bare metal framework, we can create custom tests to run, and we assessed almost all of basically all of the actual features that are mandatory in the IP.
Okay, thanks.
Last question. No. Okay, so Thanks, Luis.
Thank you.
Thanks.